Welcome back. And the topic today is a more technical one. And we are going to look at the stability of the Hartree-Fock equations. And at the same time, we are going to introduce a theorem which is called Thouless theorem. But I wanted to repeat some of the elements which we discussed yesterday, in particular in the second lecture, because the video didn't come out properly last time. So I may have to re-record it again. But let me just remind you quickly of the way you would typically implement the Hartree-Fock algorithm. So what we did yesterday was then, if we just scroll down a little bit, we went through variational calculus, and there was a reminder about that. But then in the derivation of the actual Hartree-Fock equations, we used what's called the expansion in terms of the basis. So you could think of your basis phi here as being a basis which is your computational basis. It could be a handy one, like the harmonic oscillator, if that is a relevant problem. It could be hydrogen-type orbitals. It could be a set of Gaussians if you're doing quantum chemistry. And then you can expand this orthogonal set of basis states and then set up a new wave function. So the Hartree-Fock method is a method where we now vary the coefficients. Alternatively, you can vary the wave function, as we discussed yesterday. And that leads to a set of integral differential equations, coupled ones, but they are normally a little bit more tricky to set up and solve. I mean, you can do it, but you would often need a lot of integration points. And the algorithm can be less efficient if you can calculate the integrals beforehand. Alternatively, you can also calculate them on the fly if you have a basis set which allows you to do that from a computational point of view, in the sense that you don't waste too many cycles. If you have a huge basis set, it could actually be more beneficial if you can calculate these matrix elements on the fly than to tabulate them and search for them in a table. So typically in quantum chemistry, there is a basis set which is often used for this wave function phi lambda, which is called a Gaussian basis set. That is extremely beneficial when you're dealing with molecules and you have different mass centers, because you can easily implement translational invariance. And then implementing translational invariance with a Gaussian basis allows you to calculate the matrix elements or the integrals, which is the more correct name for it, on the fly by recursive algorithms. And that is sometimes cheaper than you looking up in a table of pre-calculated integrals. So this is always a kind of trade-off of the Hartree-Fock method and any method which then looks up a table of integrals. So what we did then, by varying the coefficients, if we scroll down a little bit, just as a quick reminder here, we wrote, this is also related to the exercises from last week. So what we started with is the Hartree-Fock or the ground state energy expectation value with the reference state. And this is the expression which we derived in the beginning of the semester. And this will be with a computational basis which we have chosen. Then what we did, when we vary the coefficient, we obviously have the same equation because we have only one Slater determinant. So this equation here looks like the other one, except that now we would get an expansion in terms of the computational basis step. So the integrals which you see here are integrals which you can calculate either easily or you can look them up in a table. And then the thing which we did was to vary the coefficients. When we did that yesterday, we set up the Lagrangian because we also have a Lagrangian multiplier which reflects the fact that there is a constraint on the wave function which we are setting up. And when we did that, we ended up with an equation here which, after some manipulations, we could actually rewrite this as you would rewrite a specific matrix element times a coefficient, which is now a coefficient in the eigenvector, and then multiplied with the equal to the eigenvalue times the specific coefficient for that state I here. And when we did that, we ended up having to calculate this matrix So, and this is normally called the Hartree-Fock matrix. And it's the matrix which then reflects the medium which you have, the number of particles, the bystanding particles. And then there is a sum over all the single particle states in your computational basis. And this is something you would rewrite like this, which is simply just a standard eigenvalue problem. So you need to set up this matrix, but you see that this is an equation which is nonlinear in these unknown coefficients. And the way you solve this typically is by iteration. And by iteration, that means that you start with a guess. And the typical guess is to set up the matrix which contains the transformation coefficients or the overlaps between the new and the old basis. And assuming that this is a unitary matrix, the C's, this will be the matrix elements of a unitary matrix. And you would typically, in the Hartree-Fock algorithm, the standard approach is actually to keep the diagonal elements as the first iteration. So this is one of the standard ways of solving the Hartree-Fock equations. And that means that with that, you have an iterative scheme. And the algorithm goes like this. You start with a guess. You could also set these to be random values, as long as this leads to a unitary matrix. So the C's are complex variables. Just keep that in mind, because your wave function is a complex object. And you start with a guess, and then you keep iterating. You calculate the first Hartree-Fock matrix element. Then you diagonalize. You get a new coefficient here, where these are the eigenvectors from the diagonalization and eigenvalues. Typically, you would keep iterating this formula here till the difference between the previous and the new eigenvalues. These are the single particle eigenvalues. Keep in mind that if you wanted to, you could have another test where you actually calculate, if you go back a little bit, you could calculate the energy here, like this, because when you diagonalize, you get the coefficients. But this is much more heavy to calculate, because in the calculation of the energy, you have a quadruple sum. So typically what you would do when you set up the iterative scheme is to compare against the single particle energies. So that means that you would typically then just have a test where you terminate iteration if this difference is smaller than a given number. And this M here, this should actually be an I here, actually. This is not P, but should be an I. This is an error from my side. And M is the total number of single particle states you're looking at. And this is essentially the Hartree-Fock algorithm. And it's pretty straightforward to implement. There's a code example if you go to the Jupyter notebook. So you have both the PDF and the Jupyter notebooks. And in the Jupyter notebook, there is a code example for setting up the Hartree-Fock. But you would need then to provide these integrals. And it's pretty common, as we said yesterday, to define something which we call the density matrix, because you see now that when you're looking at the calculation of the matrix element here, or this specific contribution, you're having a triple sum, and you can reduce that one by summing over all the particles. And that means that you define an object which now contains the given single particle states, and then you sum over the states which are below the Fermi level. So you would typically call this a density matrix, and this is defined like this. And then you can rewrite this in a much more compact way. And that is something which normally speeds up the computations as well. So this is just a kind of part of the calculational recipe. So this is one of the ways of implementing the Hartree-Fock equations. Now, the thing which we are going to do today is more to look at the stability of the Hartree-Fock equation. And there is also something which we will use later. And that is Thouless theorem, which now allows us to write a general Slater determinant as a linear combination of particle-hole excitations. Keep in mind now that the Slater determinant is given by a product of single particle states. We can actually write a general Slater determinant for the ground state, which also includes one particle, one hole excitations. So let's take a look at that. And this is something which leads us to the discussion of the stability of the Hartree-Fock equation. So what I'm going to do now is just to go back to the whiteboard, and we are going to go through the basic mathematics here. Okay, any questions? So this was a quick reminder of what we did yesterday, in particular with the Hartree-Fock algorithm. Okay, so let me just switch of this one and go back to the whiteboard. So when we looked at one of the exercises last week, in that exercise, we looked at a Slater determinant in what we normally call the coordinate representation. So let me quickly remind you of what we had in the exercises last week. So if we look at the coordinate representation of a Slater determinant, so that means that we had then a Hartree-Fock Slater determinant. So this is a determinant now, the way I'm thinking of it. And what we found then is that this is proportional to the original determinant, which we had, multiplied with the coefficients or multiplied with a unitary matrix. So what we had then was the determinant of this matrix C. So just keep in mind that the single particle basis, which we are looking at, is now given by an expansion in terms of the computational basis, which we had, where we had this lambda states. Then this matrix, which you see here, is actually either an orthogonal, if these are real elements, or a unitary matrix. So that means that we can actually write it out like this. Now, this is in first quantization or just in coordinate representation. It's often a little bit more delicate to show the stability of the Hartree-Fock equations using this machinery. So with second quantization, this is something which is much more easy to show. I mean, if we want to discuss what are the requirements on the stability of the Hartree-Fock equations. So what we are going to do now is to look at the stability and what kind of requirements can we get. This leads us, in order to prove that, this is going to lead us to an intermediate step, which is called Thouless theorem. And as I mentioned yesterday, Thouless was one of the people who got the Nobel Prize some years ago in physics. So Thouless stated that we can actually write a general Slater determinant in terms of a linear combination of one particle, one hole excitations. So let's prove that first, because that is going to be essential for us in order to prove the stability of the Hartree-Fock equations. So at the end, what we are going to show, if you want to prove the stability of the Hartree-Fock equations, is that we can have a requirement which is necessary but not sufficient, where we actually look at the values of the integrals of the interaction and the one-body part of the Hamiltonian. So by looking at these specific contributions, we can say something about the stability of the Hartree-Fock equations before we have started the calculations. So let's take a look now at the Hartree-Fock Slater determinant, the way we wrote this out in second quantization. And what I'm going to do now is to write this as C. So suppose we have done the Hartree-Fock calculation. This is our new ansatz for the ground state. And it means that if we think of this in terms of second quantization, we have a product of creation operators acting on the true vacuum here. So I'm just going to use this C as a more compact notation, because else you will also go a little bit, I mean, it's going to be a lot of subscripts and superscripts and so on. So what we are going to do now is to perform a variation of that one. And this is what we did with the Hartree-Fock equations. So we are going to assume that there is a C prime, which is given by C plus a delta C. So we are going to assume that there is a general Slater determinant. And you remember from yesterday that we called this delta C as a given in terms of a parameter eta, and we had an AI, an AA and AI acting on the state here. So we create a one particle, one hole excitation. This was a kind of ansatz which we made for the Hartree-Fock variational, the implementation of the variational calculus for the Hartree-Fock equation. And when we did that, we found that the Hartree-Fock requirements from variational calculus, when we take the derivative with respect to this change delta C, we found then that we had this delta C with a Hamiltonian of C equal to C of H of delta C equal to 0. And in our case, that meant that we had the integrals over this operator F of I equal to 0, or we could actually look at the other equation. So these two equations are independent of each other, and they can be solved independently, or you can just look at one of these equations. So this is what we did yesterday. And we then found, as we have seen before, that this corresponds to us taking the overlap between the zero particle, zero hole state, where we have only one, with a one particle, one hole excitation. And the Hartree-Fock equations, which follow from variational calculus, simply gives us that this block of matrix elements should be equal to 0. Now, what Thouless did then was actually to show that this C can be written as a very general Slater determinant of one particle, one hole excitations. So there's going to be a sum over the one particle, one hole states, which we have. There is a coefficient C of IA, and we are going to label that one, since we are going to think of this as a small variation, we will put a delta C in front of that later. But this is just a general expression where we have an AI, and this is then multiplied with the ground state ansatz or reference state, which is now the Hartree-Fock reference state. So this is a general Slater determinant, which we now can express like this. And this is something which we will often rewrite in terms of a T1. So this is it contains a cluster, it's an operator. And this operator contains now the sum over all the one particle, one hole excitations of AI, AA, like this. So this is an operator which then acts on the states, and it produces a linear combination of one particle, one hole excitations. Now, when we later this semester are going to introduce couple cluster theory, which is another many-body method, then we are going to use this label T1 here. So in Thouless theorem, we can actually show that there is a general Slater determinant, which we can actually write in terms of this set of one particle, one hole excitations acting on a reference state. So let's now try to show this. And I wanted to quickly remind you of some useful relations here. So the relations which probably you remember is obviously the exponential of A plus B. And as long as A and B commute with each other, if these are operators, this is just the usage of the binomial formula. And you've probably seen this many, many times. So as long as the operators commute, we can actually write them like this. And A and B can be just numbers or operators. So this is one of the expressions which we need. Then another expression we need, if you now look at the sum like this. This is something which obviously, if you now think of the sum as xi here, a sum over I up to some element n, this is obviously x1 plus x2 plus xn. So that means that I can actually rewrite this sum, I of x of I. I can rewrite that as an x1 of e of x2, e of x3, up to e of xn. And that is nothing but the product I equal 1 up to n of e of x of I. Okay? I assume that you're familiar with this formula. You've seen the derivations of them, and that we can simply use them. I just wanted to remind you of these expressions. Okay. So let's just wait a little bit so everybody, because now what we are going to do is to rewrite this equation here using this expression. And just keep in mind now that the sum over I is finite, whereas the sum over A is infinite. So in principle, when we look at these sums, we should just remember that AI is actually a sum where I goes up to the Fermi level, and that simply runs over all the single particle states which are being occupied, whereas A starts with the states above the Fermi level and in principle goes to infinity. So one of the things which we're going to do now is to rewrite that Slater determinant, which we had, is C prime, and we are going to rewrite that as a product where we now single out the states below the Fermi level. So these are the whole states. And that means that I would have then the following: 1 plus, and then I have a sum over A of F, and then I have a CIA, and then A and AI. That's the first term. So what I'm doing now is simply, if you go back here, I'm just Taylor expanding this expression which you see here. And then I'm, for the whole states, which go from 1 to n, I'm simply using the product formula here. So that's why you see this one, but then I have to perform the summation over the infinite summation over the particle states. So this means that I would get the plus 1/2, and then I have a square term, A larger than F, and I have a CIA, and then I have my AI squared, and this just goes on to the final term, or actually to infinity, and this is acting on C here. Now there's a very interesting result here for us if we look at these different terms now. So if you look at the term, the second term, I mean, if you take the second term here now, so let's take a closer look at that one. So when we write it out, this specific term here is going to be given by the following expression. So we are going to have a term which is A larger than F, and then I have a CIA of AA dagger, AI, and this is multiplied with a new term. And since I'm squaring it, I have to have, and the summation runs over the indices A, I have to make a distinction here so that I have a subscript B as well. Like that. But the I, which you have here, is fixed because I've been using the product rule. So that means that I is always fixed here. So when I square this one, the I which I have here is going to be the same as this one. So if we write this out, and we have to keep in mind that this is going to act on the reference state. So what you see now is that you're going to have a term AB. That's going to be a CIA, a CIB, and then an AA, AB, no, sorry, A. And this is going to act on C. And what you see now is that since I is included in C, we can remove it, so that operation is okay. But then I'm trying to remove something which has been removed. So this has to be equal to 0. So what you see then is that all terms beyond this one actually give 0 results, because I have I'm not allowed to have more than one state in a single particle state. So from the squared one and higher order terms, these are all going to vanish due to the fact that this state has been removed once, and then I cannot keep removing it, because we have that A of I acting on 0 is equal to 0. Okay? So that simplifies my expression for the Slater determinant. So it means now that I can actually rewrite this Slater determinant simply as this product I less than F, and then I have 1 plus, and I have this sum A larger than F. You correct it a little bit, it's like this. And then I have CIA, and this acts on the reference state, which is now our Hartree-Fock state. Okay, so if we now write this out, so let's look at this term by term, because we are going to rewrite this equation in a more compact form. And we're going to define a new operator, and then we're going to show that although this one has a constraint, that we can actually write that as a general determinant in terms of a new creation operator, which acts on a vacuum state. So let's write this out. So the state C, which I have, is something which I'm going to write out in terms of an AI1, just to distinguish it from the I which we have here. And then there's an AI2 dagger, and this goes up all the way up to the last state below the Fermi level. So this is the way I would write that Slater determinant. Okay, so that means that if I do this, then the state C, which I have, and each one of these I's here, it corresponds, each I here is included in these I's which you have here. So just keep in mind that when we are doing this expression here, this I is included in I1, I2, I3, up to IN here. So if I now write this out, let's just switch page here so we can fill everything in just one page. So we're going to see that this C prime is going to be given by, and then I have 1 plus, and then I have a sum over CI1 of A, and then I have an AA dagger, A, so I'm just writing out the product. Previously I had the product, so now I'm just picking out every element in the product. And then I have an I1, like this, and this is multiplied with AI, sorry, I mean, I wanted to have it, let me just rewrite it a little bit, not like this. Like this, so then I have an AI1 here. And this one, that's the first term. This is then multiplied with the next term, which is 1 plus the sum over A. I'm just skipping that these sums run over states above the Fermi level. So now I have the second state, and I have an II2, and this is multiplied with I2 here. And this runs all the way down to the last one, which is 1 plus A, and then I have a CIN, A. And this acts on the vacuum state, like this. Okay, does that make sense? So I'm just taking the product and I'm picking in the product all the different contributions which I have. So since this I is now included in this set of states below the Fermi level, it means that the first one here is I1, the second one is I2, etc. Now, when I do this now, you see very clearly that since these states are different, so the reason why I've written it like this is that all these states are different, so they commute with each other. And that means that when I now take the action of this one on the vacuum, I add this one, and then I take it away. So that means that this term here gives us just the Kronecker delta, or when you take the contractions in this for these states here, that simply gives us 1. And then I have this one multiplied with that one. So I can actually write the Slater determinant in a more compact way. So I can write it as the product now of all the i's. And then I have an A, the creation operator, which comes from this term being multiplied with that one. And I do it for all the states which I have here. And then I have plus a sum over all the states above the Fermi level, and I have a CIA of AA, and this is acting on the vacuum state. So this is still us just rewriting Slater determinant, and what I could do now is to define a new operator. So I could define this as an operator which I call for a B of I, which is a linear combination of this term plus this term. But what you see now is that due to the constraint here, that means that this is not a general enough expression. So we would like to define an operator B here, which is so general that we don't need to think of a specific constraint. Okay? So I want to prove now that this is actually something which can be retraced to a more general expression where we have defined an operator B of I, which we can call for B of I tilde, which reduces to this form, starting from a general expression for a Slater determinant. So what I'm going to do next now is simply to define this operator B. So we define B, I, and this is defined as the creation operator here, plus this sum A, starting with states above the Fermi level, and CIA of AA dagger. So this has a constraint, and that means that the operator is not general enough. So in principle, we would have liked this one to run freely over all the possible single particle states. Okay, so when we then look at the Slater determinant which we have defined, it means that the C prime can be written out like this, up to n, obviously. And then we have a B of I dagger acting on the vacuum state. So when we are setting up, if you now think of the expansion we started with, so think of you defining this state lambda, and this is our computational basis, 0. And then we had a state P, which is the new basis, which could be the Hartree-Fock basis. What we found then is that this AP dagger is now given by a sum lambda, where we have the overlaps between the coefficients. And this is a general expression. And in this case, this is an unconstrained sum. There are no restrictions on the sum. It simply runs over all the states which we have in the computational basis. So what I would like to have now is something similar to this one when I'm going to define this operator and a general Slater determinant. This is the main aim behind Thouless theorem. So we're going to see that this actually can be retraced to a more general expression of this type here, where you don't have any restrictions. So let's try to prove that. So what I'm going to do now is to define a new operator. So following this philosophy, I'm going to define an operator which I call for B of I tilde, which is now simply a sum of B, and I leave this undefined, GIP, of an operator AP dagger, where this P is unconstrained, the summation here. I haven't specified these G's, except that these are going to be the coefficients of overlap between the two creation operators, and we assume that these are complex coefficients. So what we want to show, if I use this one, I can now define a new Slater determinant, and this is now going to be given by I less than F, or B of I dagger, acting on the vacuum state. And we want to show that this is a general Slater determinant, to show that this C tilde is the same as this C prime, okay? So what we have basically done here is to assume first that we can write a Slater determinant in terms of one particle, one hole excitations. We have rewritten that one and found a new operator, this BI, but this operator has a constraint. Now, in general, what we would like to have is something which does not have a constraint. And that means that we assume that there is a coefficient which brings us from the previous operator to the new operator without any constraints. So what we are going to show now is actually that this assumption which we made can be retraced to a general creation operator, and that means that this C tilde is the same as this C prime which we started with. The C prime which we started with was an ansatz, okay? So what we are doing now is just to make a transformation of the creation operators, which will then contain a linear combination of particle and hole states. So let's show that this is actually the case. So what we are going to do now, we are going to assume that when we take the overlap between C and C tilde, that this is going to be normalized to 1. So if I now calculate this C of C tilde, what I have is the following. So we're going to have a 0. There's going to be an AIN. So this is our original operator. And this goes down all the way to AI2, AI1. So this is this specific state, which we have here, with the original definitions. And then we are going to multiply that one with the new operators, the B tildes, which we had. So that is going to give us then the following. So there's going to be a term here, which starts with a P equal to 1 up to IN, the last state below the Fermi level. And this is going to contain the first one, which is a GI1 with this coefficient P, and then AP dagger, like that. This is going to be B1 or BI1, as we called it, dagger tilde. So just keep in mind that our Slater determinant, this C tilde, is now given by the product of all these states of BI dagger tilde acting on 0. So what I'm doing now is simply to set in the expression here. So I have a linear combination between the previous operators and the new ones. So simply setting it in for every single particle state below the Fermi level. So this will then contain, in the next term, it's going to contain a sum where I'm going to put Q equal to 1, and then up to IN, the final one. And this is going to have a GI2 here. And and then it's going to contain the term Q, and then it has the AQ dagger. And this continues all the way up to the final one, where I'm just going to write this as a T of IN, and then I'm going to have a GIN, and this is multiplied and T, and then AT dagger, and then acting on 0, like that. So that's the overlap between this new determinant and the old one which we have. Now let's look at an example now. Let's assume that you have only 2 states below the Fermi level, because then you can see immediately what we are going to get. So let's just wait a little bit so people can write down. So let's now pick a case where we take 2 states. So that means that we have an I1, which I'm just going to use 1 as a label for, and then an I2 here, which I'm just going to write as 2 in the equations. So that means that the sums which you see here are going to run from 1 up to 2. So let's try to write this out. So what we will see then is that we will have 0, and then there's A2, A1. So this is the original state. And then what I'm going to get is the following. If I now just write it out, I will have a G11 times A1 dagger, and plus a G12 times A2 dagger. And this is multiplied with, and then I have a G21 A1 dagger, plus a G22 of A2 dagger, acting on 0. So what I did was to take the general expression, which you had in the previous equation, and then just specialize that to 2 states only. Now, if you look carefully at what we have here, there are some interesting things which we can actually generalize to more than just 2 states. But you will see that the final result coming out of this expression immediately. So this is going to be equal to 0, and then I have an A22, no, sorry, not A22, but A2 and A1. If I write this out now, what I'm going to have is G11, A1 dagger, and G21, A1 dagger, plus G11, A1 dagger, and G22, A2, plus, and then I'm going to have a G12, A2 of G21 of A1 dagger, plus G12 of A2 of G22 of A2 dagger, and these all act on the true vacuum. So let me now ask you, before we take a small break, what is this one going to give us? And what is this one going to give us? Yeah, just zeros. So you see now that these 2 terms here, they just give us zeros. Now, I want to have everything in a normal ordered form. And I also would like to have a hierarchy where I start with A1 dagger and multiply with A2. And what you see now is that this one has an A2, A1. Okay. So I just interchange the 2. So I can actually write this out as 0, 0. No, so 0. And then I have my A2, A1. And then I have an interesting term here. There's a G11 times G22 minus G12, G21. And then I have an A1 dagger, A2 dagger, acting on 0. What is this guy? Think of a matrix, and you can calculate something from a matrix, which begins with the letter D. That's a determinant. That's a determinant of that matrix G. And you can show that if I were to take 3 states, you would got a 3x3 determinant, and so on. So this is actually quite interesting. And we're going to stop there. And then after the break, we are going to show that using that properties and the properties of the matrix elements of a determinant, we can actually show what we wanted to originally, and that is to show that the one we started with is actually a general Slater determinant. So what we have here, if you now also look at the contractions, when I take this one, that obviously has to go to that one, and this one has to go to that one. So that means that when I look at it, this is simply just the determinant of G, which is the same as G11, G12, G21, and G22. So if you were to look back at the more general expression, this is something you can see easily if you do it for a 3x3 determinant, a 4x4, etc., etc. So this is actually quite interesting because we have required that we have a normalization. And this normalization is that C of CD tilde is equal to 1. And you see now that this is to be the same as this determinant of G, if we require that as a normalization condition. Okay, so after the break, we are then going to show the final steps in Thouless theorem, that the one which we started with, which is a general one particle, one hole excitation, is actually a general expression for a Slater determinant. And that becomes very handy when we want to show the stability of the Hartree-Fock equations, which is a step after the break. So we just need some few lines more to conclude Thouless theorem. And with that one, we can start calculating expectation values, and then we will prove the stability conditions for the Hartree-Fock equations. Okay, so let's just take a small break. Okay, so let's try to wrap up Thouless theorem. And what we need to remind ourselves is a little bit about the determinant and some properties of the matrix elements of the determinant. So let us quickly do that. So we know that for determinant, if we take these elements, if we sum over the elements J here and take GKJ inverse, this is going to be equal to delta IJ. Now this should be a sum, sorry, this is a sum over K. I just wrote wrongly here. A sum over K, this is the same as delta IJ. And similarly, if I set up a summation over J here, over all the elements, so these are just some basic elements of relations for the determinant. So this is the same as delta IK. So what I'm going to do now is to define this operation here, because this is something which we are going to have in the expression we put up. If I take minus G minus times B of I, this is going to be the same as the sum over I, and then I have a GKI minus 1, and then I have a sum over P, where this sum goes over all the possible states which I have. It starts with 1, and in principle, this goes to infinity, okay? So what I'm doing now is to bake in my general summation with no constraints at all. So this is going to be given then by GIP and multiplied with the creation operator. So this is what we have here. This is just a definition of that specific operator which we put in. So when we now use the properties of a determinant here, and these specific normalization conditions, when we do that, we can actually rewrite this one as follows. So this is something which we then can write out as an AK dagger plus a sum over I, and there is a summation over P, where we now simply have split this one into an I of n plus 1, so this is above the Fermi level, and infinity, and then I have a GKI inverse here, GIP, and this is multiplied with AP here. dagger. So what I could do now is just to define a coefficient, which I call CKP, which is simply the sum from I less than F, and then I have this GKI inverse, and then GIP. I redefine that one. What I have then is that I can rewrite the equation, the previous one, the first line above, as an AK dagger plus a sum over P equal I n plus 1 to infinity in principle, and then I have a CKP and then an AP dagger. And this K is obviously assumed to be below the Fermi level. Now, this is nothing but the operator which I defined earlier. So earlier we defined an AK dagger plus this summation over A larger than F, the Fermi level. And then we had a CIA. So actually this is an I here, just to remind me, because we use an I then, plus an AA dagger. And this is what we called for this creation operator for B of I dagger. So what I have now is, this is the expression I have from the general Slater determinant. This is an unconstrained summation. So the only thing I did was actually to rewrite this operator, which I defined, this B of I, which is my general one. And then I just rewrote it in terms of a new set of terms here, which I redefine as a coefficient CKP. And then I can rewrite the first line above as this. And that is nothing but the original operator which I put up. Actually, I should be a little bit careful here because this was my BI tilde. Sorry for that. So if we go back a little bit, what we did then was simply to define this BI tilde as this linear combination here, where this sum is unconstrained. So in principle, when I'm setting up a general operator like this, I would not like to have any constraints on the definition of the operators, because my operator, the way I put it up here, when I define this BI here without the tilde, this has a constraint on the summation. So what I would like to have is something which is just unconstrained. And then I started with this definition. But then due to the orthogonality requirements which we have, we can then actually show that this operator which I have, this BI tilde here, when I rewrite everything, I can actually get back the operator which I started with. So that Slater determinant which I defined is actually a general Slater determinant. So my C tilde, which I have, which I defined in terms of a sum up to the Fermi level of BI dagger acting on the true vacuum. This is the same as this operator which I chose to represent a linear combination of particle-hole excitations. And this is the same as a BI dagger acting on the true vacuum, and where this BI is now simply us setting up an AI plus an overlap here, and then AI dagger, and then a summation over all states above the Fermi level. And that summation which you have here, in principle, that runs to infinity. But when we are going to run actual calculations, we will always put in a truncation here. And this is essentially Thouless theorem. If I do this, then that means that this is a general Slater determinant. So the exponential of the sum over AI, and then I have the CIA, and then AI dagger, AI. And this acts now on a given reference state. So this is a general Slater determinant, and this is essentially Thouless theorem. So what I have in principle here is actually a product of one particle, one hole excitation. And this represents a general Slater determinant. Okay, so why is this useful? This was a long detour to get to what is the central topic here, is to study the stability of the Hartree-Fock equations. So what we need to show now, because when we have run a Hartree-Fock calculation, we don't know whether this minimum or this new ground state which you have found, if that is a good minimum or not. So what we have calculated is this, which actually is now phi0 Hartree-Fock, just to remind you of that, the full notation which we have been using. And we call this E0 Hartree-Fock. We can also call this, and you will see that that is the standard notation. This is the new reference, and people would put in Hartree-Fock, the reference state with the Hartree-Fock basis. So the reference state is calculated for one Slater determinant only. So just keep in mind that although this is a Hartree-Fock basis, it's actually given by one single Slater determinant. So we are going to call this the reference, the new reference energy. Okay. So we are now asking ourselves, is this actually a better minimum than the one we would have gotten? So ideally what we want is that this guy here should be smaller or equal to the one we started with. So phi0 is our original ansatz in the computational basis which we have chosen. So what we want to show now is that any variation of this state actually leads to us concluding that this is an optimal minimum with the kind of variation which we are going to do. So let's now look at the calculations which we did. So our Hartree-Fock basis is given by this expectation value. This is what we get. This is the new reference energy. And in the Hartree-Fock calculation, what we have found is that a variation of the state, so this leads to the Hartree-Fock conditions, this is equal to 0. In our case, just to remind ourselves of what that means that's a one particle, one hole block with phi0, or the 0 particle, 0 hole excitations, is actually equal to 0. Okay? So when I say 0 particle, 0 hole, that is my reference state. Now, what we are going to ask ourselves now is the following. So we define this new Slater determinant, which is going to be given by this delta C term. And when we now use Thouless theorem, we are going to have this one equal to the exponential of the sum AI. And now instead of writing C, I'm going to write it as a delta C. So we are making a small perturbation of these terms. And then we have an AI dagger, AI, acting on the Hartree-Fock state. So that means that my delta C is simply going to be a linear combination of one particle, one hole excitations. And this goes back to the original ansatz which we made yesterday when we looked at the way we can interpret this one. I mean, there's nothing which hinders us in including two particle, two hole excitations, three particle, three hole, etc. But that will definitely complicate everything. And you will not get a set of coupled single particle equations if you include two particle, two hole excitations. Sorry. So let's now look at the requirements, because this basis C prime is not normalized. So when we now calculate the expectation value, and this is the equation we want to prove or use as a basis for looking at the stability of the Hartree-Fock equations. So what we are going to require now is that this should be larger or equal to the Hartree-Fock energy. So which is the same as our E0 Hartree-Fock, or just a reference energy. So we make a variation, and then what we want to show is that the term which has not been varied gives a lower energy than the one where we make a variation. Okay? So this is a starting point for studying the stability. So what we are going to do now is just an exciting exercise in second quantization and contractions, etc. And we are going to calculate the different terms here. But then we are going to truncate everything at the level of this delta C squared. So let's look at the denominator. So we have not assumed that these C primes are normalized to 1. So that means that when we calculate them, we need actually to be a little bit careful here. So if I look at C, so let's take the denominator first. C prime of C prime. And what does that one look like? So now we're going to plug in the expressions which we have. And what we need to do then is simply to go back here and look at what this term looks like. So this term is going now to be, if we Taylor expand it, there's obviously 1 times this one. So that will obviously give me, there's going to be a 1 here. Then when I now Taylor expand it, there is obviously going to be a term which contains this guy here to first order, that one. But then when I take the expectation value of this one acting on that one, I create a 1 particle, 1 whole state. But then there's going to be a 1 first here. So the terms with the delta C to the power of 1 are going to disappear, because in that specific case, I'm going to have a C times an AI acting on C times a delta C AI. And that one is obviously 0, because now I create a 1 particle, 1 whole state. And this is a 0 particle, 0 whole state. So if you think back to what we discussed earlier, that you can actually look at what kind of states the operator creates, and then see if you can match that one with what you have on the brass side. So in this case, you're trying to match 2 states which are different, and that is obviously equal to 0. So that means that the next term which contributes has to be a term of the form. So let's just write this down. So there's going to be a new term which goes like an A, B, I, J. There's going to be a delta C, I, A, complex conjugate, a delta C, J, B, like that. And then I'm going to have C, and then I will have an A, B here. And then there's going to be an AJ, an A, not J, but I, A. And then I have an AB and an AJ acting on C. So that's the next term I'm going to get. It's because the linear terms, they disappear by obvious reasons, because then I'm trying to calculate the overlap between a 1 particle, 1 whole, and a 0 particle, 0 whole state. In this case, I create a 1 particle, 1 whole state, and then I destroy a 1 particle, 1 whole state. And the contractions which survive, the only ones which are actually possible, are these ones. So you see then that the sums are reduced to a double sum. So that means that this term here becomes simply a sum over A and I, and then I'm going to have a delta CIA squared. Now, in the calculations now, we are going to assume that delta C is small. And we are going to leave out terms higher than delta C squared. So, but if we now write this out, what we are going to get, so we have additional terms here. So we are just going to write this out as a 1 plus an AI, and then I have my delta CIA squared plus higher order terms, which I'm just going to write like a delta C cubed. And we are going to ignore them later. Okay, so that was the denominator. Now we need to look at the numerator. So let's take C prime of H of C prime. So that is going to contain the following terms, which we have to look more carefully at. So this is going to have a term which is C of H of C, like that. This is nothing but what we call as a reference energy, or in our case, the Hartree-Fock energy. Then there's going to be a term which goes like a delta C of H of C plus a C of H of delta C. And then finally, we are going to have terms which now contain the delta C's to different powers. But now we have to be a little bit careful here because there were going to be different contributions. So these two terms here, so there's going to be a 1, which is delta C of H of delta C here. Now this term here is going to be 0, and this is going to be 0 because these are the Hartree-Fock terms, which we have defined to be 0. So the terms which are linear in these coefficients delta C, they disappear. But when I'm now writing out these operators, I have to be a little bit careful because this term here is written in a little bit sloppy way. So this one is what we are going to get. When we now are making the Taylor expansion of the operator, we have to be a little bit careful. So let's now look at the term which we can get. So this delta C, which I wrote out in a little bit sloppy way, is actually not exactly equal to a delta C complex conjugate on the left and on the right, because what I'm doing now, if I look at my state, which I have, this state C, it will contain higher order terms in delta C. So what I will get then is the following. So this will contain one term where I have a AI and some BJ, and then there's going to be a delta complex conjugate CIA. There's going to be a delta CJB, like that. And this is going to be given by 0. No, sorry, C. And then I have my AI dagger, AA. I have the Hamiltonian. And then I have an AB, AJ times C here. But then I'm going to get a higher order term. One which comes from the ket side, because I'm keeping terms to delta C squared. So that means that there will be a term which is going to look like this. So this comes from the ket side, where I have the state squared, BJ. And then I'm going to have now a part which goes like a delta CI. So this is not complex conjugate. So this comes from the ket side. And then I'm going to have a state C. I have my Hamiltonian. And then I have an A, a one particle, one hole. And then I have an A, B, AJ. And this is acting on C. So I said that I wanted to keep contributions in the expansion of the wave function. So this notation here is a little bit sloppy, because what I'm doing now when I'm setting up the state here is that I'm going to keep terms up to delta C squared. Then I'm going to get a term like this one, where you see now that here I create a one particle, one hole state. Here I have a one particle, one hole state. And then the Hamiltonian has to match what has been created here and what is being annihilated here. Now here, on the other hand, I'm acting on the vacuum state and I create a two particle, two hole excitation. And then the Hamiltonian has to match a two particle, two hole excitation. So if we go back to what we discussed earlier, that means that, for instance, in this term here, there's only the two body interaction, which can eliminate a two particle, two hole excitation. And then I will also get a term which goes like plus 1/2, and then I have an AI, BJ again, but now I have the complex conjugate guys. And this is multiplied with the C. But now what I'm going to get is the following. So I will have now an AJ dagger, and I'm going to have an AB, and then I'm going to have an AI dagger, an AB, and this is an AA, and then I have the Hamiltonian acting on this one. So what we need to do now is to calculate these different terms. So let's just put the labels on them. So I'm going to label this as 1, and I'm going to label this as 2, and I'm going to label this as 3. So let's look at the first one. And here we now need to set up the Hamiltonian itself. So what the first term is going to give us, if we now remind ourselves about the expression for the Hamiltonian, so the Hamiltonian is given now by the reference energy, which is our Hartree-Fock energy, plus this one-body operator, so this is with respect to the new vacuum, plus the two-body operator. So let's look at the first term. So the first term has a structure which goes like, so what I'm going to do now is just to set in the terms, and I will not carry with me everything, but let's just set it up because we are going to have a sum over AB ij. I'm going to have a delta CIA, and then a delta CJB, like this. And then this is going to be multiplied with C, and then I have my state here, which is, if we now look back and have an AI dagger, so there's going to be an AI, an AA, and then I'm going to have E0, Hartree-Fock, plus this F of N, plus V of N, and this is multiplied with AB, AJ, and then acting on the true vacuum, on the reference state. So I'm using this C now for my reference state, which is actually the Hartree-Fock state. Just remember that this one is actually phi 0 Hartree-Fock. Now, if we take the first term, so let's look at the first term. And now we're going to just write this out in terms of the operators. So in this particular case, this contraction gives us a delta AB, and that contraction gives us a delta IJ here. Okay? So it means that this term is pretty simple. So I'm just going to get a sum over AB IJ, and then I have a delta AB. So if you look at the sum here, so this is simply going to be given by a single sum over A and B. So we can just write it out here. So that will contain a sum over AB, no, so AI. Sorry for that. So I have an AI, and then I have the coefficient delta CIA squared times Z0 Hartree-Fock, which is just a constant. That's what I get here. That's the first term. Let's then look at this specific term here, because that's a one-body operator. Okay? So the one-body operator, when we take that one, so is it okay if I change page or just wait a little bit? Okay, let's just wait a little bit. So if I take the one-body operator, this is going to contain a term like this one, where I have C, and then I have an A, I, A, and then I have a sum here over P and Q. So let's only look at the operator terms. And then I have my AB, and then my AJ here, acting on the vacuum state. Now, the possible contractions which I have is that I can have the particle states being contracted like this. And then the only other possibility is that the two whole states end up being equal. So this is going to give me a delta IJ multiplied with a delta AP and a delta QB. That will give me a contribution which goes like A of F of B times delta Ij. So the double sum of P and Q disappears. Now there is an important aspect here, and that is that with the Hartree-Fock basis, we have now assumed that F acting on a state P is equal to the Hartree-Fock energy times P. So our new basis is an eigenbasis of this Hartree-Fock operator. So that means that this specific term now becomes equal to delta AB, and then I have simply epsilon Hartree-Fock, epsilon A Hartree-Fock, multiplied with delta Ij. So that's one term. Now, if we now look at the next term, which we can have, and this is the only other possible contraction which is non-zero. So let's just write it like this. Now, what I can have now is that this contraction can be non-zero, but then this contraction also can be non-zero, and then the two particle states have to match each other. Now, in order to get the operators standing by each other, then we have to permute some of them, and we get a minus sign. So this is actually going to give us minus delta AB, delta Ij, multiplied with epsilon I Hartree-Fock. So that's the second term. And if we now collect that one, and we're going to put in the final expression, what we need to keep track of is the fact that we also have these coefficients here. So the double sums are reduced to, the quadruple sum is reduced to a double sum because A has to be equal to B and I has to be equal to J. So we have the first term and we have the second term. And now let's look at this term here. So that's the last one here. So if we look at that one, what we are going to get is a sum of a PQ RS. There's a factor 1/4. There is an integral. And we're assuming this is anti-symmetrized. And this is multiplied with, and then we have an AI dagger, AA. And then we have the operators AP, AQ, AS, AR. And then I have my AB and AJ with C. Now, the possible contractions we have here is obviously that we can now set one of these operators to be contracted with that one, and that works fine. And I can have this one acting on that one. Finally, I can now have this operator here being contracted with a whole state here. And that means that the only one which is left is actually this one. So that gives me a delta IS. It gives me a delta AP. It gives me a delta QJ. And it gives me a delta, finally, a delta RB. That translates into a matrix element, because also I have to be a little bit careful, because here, since I have a crossing fermion lines, I need to interchange one of them. So there's going to be a minus sign. This is an anti-symmetrized matrix element. So what I'm going to get then is something which looks like this. I have an A, and I have my state J, I have my V, and then I have my state SR here, which is B, and then I have my S here, my I, like this. This is anti-symmetrized, and I can actually rewrite this one as 1/4 of AJ, of V, and IB, because this is anti-symmetrized. Now, there are 3 more contractions. They are all going to give the same expression with minus signs or plus signs, plus 3 more. And now I take this liberty of saying this is something I leave as an exercise to the reader. That's actually you setting up the 3 remaining contractions. It's not so exciting. This is actually straightforward. So that means that what I will get then is 4 expressions which are the same. And this is going to have an AS there. So this is going to give me the following final term. So the first term gives the following. Reads. So I'm going to have a term here, which is a sum over A and I. It's going to have a delta CIA squared. And it's going to have then a term, which is E0, Hartree-Fock. And then I have plus, and then I have the terms epsilon A, Hartree-Fock, minus epsilon I, Hartree-Fock, like that. So that's the first part. But then I'm going to get a new part here, which is going to be given by plus, and I'm going to have a summation over AB and IJ. And now I have to keep the quadruple sum. There's going to be a delta CIA, complex conjugate, a delta CJB, and this is multiplied with that specific matrix elements, which is now an AJ of V of BI here, anti-symmetrized. So that's the first term. No, sorry, the first term which we have here. Okay, so let's look at the second term. And the second and the third term, they're actually going to be pretty similar. So let's take the second term here. So the second term is going to be of the type now where I have created a, if we look back a little bit, what I'm going to have now is a 2-particle 2-hole state of this type. And then I'm going to have, in the Hamiltonian, I'm going to have a constant. I'm going to have a 1-body operator, and I'm going to have a 2-body operator. So let's look a little bit more carefully at the basic structure of that one. And what I'm going to do now is just to set this up in a much more compact way, and where I only pick out the relevant terms. So the second term is going to contain something like this. So it's going to be a C. There's going to be an E0, Hartree-Fock. We will have the 1-body operator, Fn, plus V of n. And this is now multiplied with AA, AI, AB, and AJ with C. So if we look at the first term, this one, this is just a constant. We have actually calculated this term before, because this is what you basically have here is the overlap between a 0-particle 0-hole, the Hamiltonian, and a 2-particle 2-hole state. Because you see now that this specific chain of operators, this creates a 2-particle 2-hole excitation. I can always rewrite it. So this one is something which I can rewrite as an AA, AB. I interchange B and I, and then I can put it up in an anti-symmetrized way, and it looks like this. And this is nothing but a 2-particle 2-hole state. And we know then that with a 2-particle 2-hole state here, and then a constant and a 0-particle 0-hole state, it shouldn't come as a surprise that that term is 0, right? Does that sound reasonable? Then, if you look at the next term, which is a 1-body operator, so this one will have AP dagger, AQ. Now, this state here, acting on the vacuum state, can produce at most a 1-particle 1-hole state. So then I will have, with Fn and this one, I can create a 1-particle 1-hole, which has to be matched with a 2-particle 2-hole. So that's also 0. So the only term which survives then is actually the one which has a 2-body interaction. So what we get then is, for the second term, And we have already calculated that before. So we are going to have a term which is going to be given by a PQRS. So we calculated this one 2 weeks ago, actually. So we're going to have an AP, AQ, AS, AR, and then there's going to be an AA, an AB, AJ, AI of 0. No, of the new vacuum state. So the second term is simply going to give us a matrix element. So this is also multiplied with a PQ multiplied with PQRS. So this is simply going to give us a contribution where I now have IJ actually. So one of the possible contractions is this one, and there are going to be 4 in total which are non-zero. So this contraction here is going to give us in total, when we now use anti-symmetrized matrix elements, I'm going to get IJ, V, AB anti-symmetrized. So my second term is simply now given by the sum over AB, IJ, CIA, delta CJB multiplied with this specific matrix element. And it shouldn't come as a surprise that the third term, which also links a vacuum state, 0 particle, 0 hole, with a 2 particle, 2 hole state, the third term is going to be given by ABIJ, but now I'm going to have the complex coefficients, CJB, and that is going to contain AB, V, IJ. Okay, this is as far as we got today. I would still need another 15 minutes to conclude it. So I'm going to postpone that to next week, and not to abuse on your time, guys. But the thing which we are going to do then is simply to bring these back into the equation which you see here. So we have now evaluated all these terms. We are going to keep terms to second order in the coefficients delta C. So we keep only these types of terms, this one, that one, and then we have this specific term here, plus these two. And we are going to bring them back again into the expression for this one. So let me, if I can sneak in 5 minutes, then we can set up the final expression without having put the necessary condition. So if I can just sneak in 5 minutes, I can set up the final. So if I bring everything together now, I'm going to have the expression here. I multiply this one up here. I have calculated this one. I found that one here. I keep terms only to delta C squared. So if we do that now, if we collect everything, what we are going to get is the following. So let me just set this up. So if I write this out, this C prime of the expectation value of C prime of C, this is something which I now can approximate with an E0 Hartree-Fock plus, and next week we are going to set up all the details here. Wait a moment. No, let me just rewrite it without the denominators. If I take this term here, I can rewrite this one when I keep terms only to delta C squared. I'm going to get the Hartree-Fock energy of 1 plus, so that was the first term, and then I have this AI term, and this is the same as the denominator which we had, CIA squared, plus a term delta E, plus some higher order terms. But we are going to skip those high order terms. In principle, then I should put this one equal to But if we skip those, then what we are going to have then is the following, because this is nothing but the normalization constant, which we defined earlier, C prime. So that means that what I'm going to get then, if I divide by this one, I'm going to get that C prime of H of C prime divided by C prime of C is going to be equal to E0 Hartree-Fock plus delta E divided by 1 plus the sum of AI, and then I have a delta CIA squared. There's an approximation when I keep only terms to delta C squared. Now, what we have not defined now is delta E. So delta E is going to be given by these different terms. So this is going to contain the first term we discussed, the second, and the third term. And next week, we are going to look at the explicit terms and say something about the stability of the equations with respect to the integrals which we have and the single particle Hartree-Fock energies. But you see now for this one to be the ansatz for the best possible ground state, delta E has to be larger than or equal to 0. So for delta E to be a minimum, for E0 to be a minimum, we need that delta E is larger or equal to 0. Next week, we are going to translate this into a matrix, and that means that the matrix has to be semi-positive definite, which means that the eigenvalues of the matrix have to be larger or equal than 0. There is a necessary but not sufficient condition that if you sum the diagonal elements, they have to be larger than 0 or equal to 0. And that puts a constraint because we are going to see that this matrix, the diagonal elements, so we haven't done this analysis yet, but we will do it next time. The diagonal elements will be proportional to EA Hartree-Fock minus EI Hartree-Fock plus some AJ, V, BI here, anti-symmetrized. So the diagonal elements of that matrix have to be larger or equal to 0. That is a necessary but not sufficient condition for the matrix to be semi-positive definite. But this is something we will finalize next week. And this will roughly take us some 15, 20 minutes. And then after that, we are going to move over to a classical system, which lays the foundation for density functional theory. And that's called the electron gas. So the electron gas is one of those cases where you can calculate analytically the Hartree-Fock energies. And you can calculate analytically, it's an infinite system. You can also calculate analytically the total Hartree-Fock energy. And that system is a system which gives a pretty good match with the many properties of metals. And it lays also the foundation for the approximation, the first approximation to density functional. So we're going to spend some time on this system. It's an infinite system of electrons with a continuous background of ions. And it's being used as a model in condensed matter physics and semiconductor physics as a model for describing the diffusion of electrons in a medium and the properties of the conducting electrons. And it's been very successful because it gives a pretty good result compared with the experiment. For us, the interesting thing is the link with density functional theory and also the fact that we have analytical Hartree-Fock energies and analytical energies for the Hartree-Fock ground state energy. And this is something we will spend some time on next week and parts of the week thereafter. Okay? So that's just anticipated. And then next week we finalize the discussions of delta E.